On Mars right now there is a canyon called Valley Marineris that runs about as long as a whole continent is wide, and it has been bone dry for longer than there has been life of any kind on Earth. Water cut some of that ground. There were rivers here once and standing lakes and a sky thick enough to hold weather, on a world that today is a freezing rust-coloured desert where the air is thinner than the near emptiness above our tallest mountains. Mars is what is left after a living world stops being one, and the part we do not like to say out loud is that Mars is not some strange or foreign case. It formed beside ours, out of the same cloud of dust at the same time, and it simply reached the ending first. So tonight I am not going to treat Mars as another world. I am going to treat it as a photograph of our own, taken from further down the same road. The question is not whether Earth ends the way Mars did. The question is how far down that road we already are. Tonight we are going to follow the exact road Mars took to its ending, and measure how much of that same road Earth has already travelled. By the end of this you will understand why Mars died, why its death was not bad luck but the ordinary fate of a small rocky world, why Earth is walking the same path by a slower and partly different route, and whether anything we could ever do would stop it. I am not going to pretend the honest answer is comfortable, because it is not. But it is far more interesting than the version where all of this is our fault and all within our power to fix. If you find yourself thinking about this kind of thing when you ought to be asleep, a quick subscribe keeps more of these coming your way. Now, let us begin. Right now, on the surface of Mars, it is about 60 degrees below zero on an ordinary day, and colder than that through the night. The air above the ground is so thin it barely counts as air at all, under 1/100th of the pressure you are sitting in as you listen to this, thinner than the near vacuum you would find far above the highest mountain on Earth. If you stood there without a suit, the moisture would boil off your skin and your blood while you froze, both at once, because the air is too thin to hold liquid water and too cold to keep it warm. And overhead there is no blue at all. The sky of Mars is a dull butterscotch tan in the daytime, the colour of fine rust hanging in the air, because the whole planet is coated in oxidized iron dust, and the wind lifts it into a haze that never fully settles. That is Mars today, a freezing, rusted desert under a dim orange sky. Lead with that, because it is the fact the whole video hangs on. Mars is not a place that is difficult to live on. Mars is a place where nothing lives, and nothing has for a very long time, and the surface tells you why the moment you look at it properly. Cut across that rusted ground and you find something that should not be there on a bone-dry world. You find riverbeds, not metaphorical ones, not vague channels, but the unmistakable branching shapes of water that once flowed, dry valleys that wind and fork exactly the way rivers fork, feeding into wide flat basins that were once standing lakes. You find deltas, the fanned-out deposits a river leaves where it slows and drops its load of sediment into open water. And the only thing that builds a delta is a river running into a lake or a sea. The water is gone now, every drop of it off the surface, and yet the plumbing of an entire wet world is still carved into the rock, waiting, like the tide marks left on a shore after the tide has gone out for good. The largest single scar is the one we opened on, Valles Marineris, a canyon system so long it runs about as far as a whole continent is wide, and so deep that in places the walls drop far below anything on Earth. Stand at its edge and the far side is beyond the horizon, hidden by the curve of the planet. It is one of the largest canyons in the solar system, and while not all of it was cut by water, water worked on it, ran through parts of it, pooled and drained and left its marks. And then, at the poles there is ice, great layered caps of it, water ice and frozen carbon dioxide stacked in pale sheets, holding a memory of a wetter world locked away in the cold where it can no longer do anything. There is more that marks Mars as a world that lost something rather than one that never had it. Scattered across the planet are basins that were plainly lakes, and in at least one of them, a crater called Jezero, a fossil river delta, sits fanned out against the old shoreline exactly as a delta on Earth spreads where a river meets the sea, its sediment sorted and layered by water that has not flowed there in billions of years. And the surface is not merely dry, it is actively hostile to liquid water in a way worth understanding. The air pressure is now so low that water cannot stay liquid in the open at all. Warm a block of ice on Mars and it does not melt into a puddle. It turns straight from solid to vapor and drifts off, because there is not enough weight of air pressing down to hold a liquid together. So even the buried ice at the poles and under the soil cannot run. It can only sit or slowly vanish into the thin sky. Mars is not just a world that lost its water. This is now a world where the conditions for surface water have been switched off entirely, held shut by the very thinness of the air the sun stripped away. And the whole planet is restless in the one way a dead world still can be, in its dust. Every so often a storm lifts that fine rusted powder off the ground and spreads it until it wraps the entire globe, blotting out the surface for weeks under a sky gone dark and orange. It is not weather in the living sense, no rain, no water, just dust driven by a thin, fast wind. But it is enough to bury the solar panels of anything we land there, and enough to remind you that even the corpse of a world has some movement left in it. Around all this circle two small dark moons, Phobos and Deimos, lumps of rock only a few kilometers across, themselves airless and cratered and going nowhere, the larger of them slowly spiraling inward on a path that will one day tear it into a ring. Even the moons of Mars are dead things drifting toward endings of their own. Every so often someone finds a hint that a trace of liquid might still appear on Mars for a moment. Dark streaks that creep down certain slopes in the warm season. And for a while these look like brine, water so loaded with salts that it could stay liquid briefly, where pure water could not. The current reading leans more toward dry flows of sand and dust than toward running water. And the argument is not fully closed, but notice how far the goalposts have moved. On a world that once ran rivers into a sea, the live scientific question is now whether a few damp streaks of salt water might survive for an hour on a warm slope before freezing or boiling away. That is the measure of how completely the water has gone. Not oceans, not lakes, not even reliable frost, but a debate over whether the planet can manage a smear of brine, and the cold underneath it all is relentless. A summer afternoon at the Martian equator might, at its warmest, briefly nudge above freezing right at the surface, but the air a meter higher stays bitterly cold, and by night the whole thing plunges to 80 or 100 degrees below zero. It is a world where the ground can thaw at your feet while the air freezes your breath, because the thin atmosphere holds almost no heat at all. All of it together tells one story, and the story is not that Mars is a dead rock that was always dead. The story is that Mars is the corpse of a world that was once alive in the way that matters, a world with water moving across its face and a sky thick enough to hold it there, and that at some point all of that stopped. I want to be honest about the edge of what we know here, because it matters for everything that follows. We are still arguing about exactly how much surface water Mars held, and for how long it held it. Some read the evidence as oceans and long-lived lakes and rain running for hundreds of millions of years. Others read it as colder and more fitful. Water that came and went, ice that melted in bursts and refroze, less a blue world than a frozen one that thawed at the edges. That argument is real, and it is not settled. But notice what is not in dispute. Nobody who looks at those riverbeds thinks Mars was always the dry, rusted desert it is now. The disagreement is about how wet and for how long, not about weather. Mars had far more water and far more air than it has today, and it lost nearly all of both. That much the rock states plainly, and it cannot be argued away. So already the common picture of Mars is wrong in a way that matters. Most people carry Mars around in their heads as simply a different sort of place. A red planet that is cold and dry because that is just what Mars is, the way some planets are gas and some are rock. But that is not what Mars is. Mars is a world that had its moment and then went quiet, and the quiet came later, and the going quiet is the whole subject of this video. Because if Mars was once a wet world with a real sky, and is now a frozen desert holding its old rivers as fossils, then something took the water and the air away, something emptied it. And the question that should make the hair on your arm stand up is not what was Mars, but what happened to Mars, and whether the same thing is one day going to happen here. Look at the planet from a little way off, and there is one more detail that will run through this whole video, so let me plant it now while it is small. Turn Mars so you are seeing it edge on against the black of space, and look at the very rim of the disk, the line where the solid ground gives way to the dark. On a world with an atmosphere, that edge is not sharp. There is a thin band of light hugging the curve, a faint glowing arc where sunlight is passing sideways through the air. That arc is the atmosphere seen from the side, and its colour and its thickness tell you at a glance how much sky a world still has. Around Mars, that arc is there, but it is thin, and it is the dusty tan of that oxidized haze rather than any healthy colour. It is the faint remnant of a sky that used to be far thicker. Hold that image. That thin tan line on the edge of Mars is the ghost of the atmosphere that once kept the rivers running. And by the end of this, you are going to have watched that same line thin on other worlds, and you are going to understand exactly what it means when it does. For now, sit with the plain fact of the place. A freezing desert, air you could not breathe and could barely call air, a rust-coloured sky, and underneath it the drainage map of a lost ocean world carved into stone. That is the after. Somewhere in the past there was a before, and the honest question is how you get from one to the other, and whether the road only runs in one direction. Before we can ask what killed Mars, though, we have to be sure there was really something there to kill. We have to know whether Mars was ever genuinely a living sort of world, or whether those riverbeds are the ruins of something far more modest than they look. So let me take you back, as far as the evidence will honestly let me, to Mars when it was young. Did Mars once look like Earth? Roughly 4 billion years ago, Mars was the most Earth-like world in the solar system after Earth itself, and it may have been the more inviting of the two at the time. That is the fact to start with, and it is a strange one to say out loud about the frozen desert we just stood on. But the evidence for it is written all over the planet, and it is the reason Mars is the honest mirror for our own world rather than just another dead rock. When the solar system was young, Mars had liquid water on its surface, moving water, enough of it and stable enough for long enough to carve the river networks and fill the lake basins we still see. Water that flows and pools and stays is water under a real atmosphere, because without enough air pressure and warmth, liquid water cannot exist in the open at all. It either freezes solid or boils straight into vapor. So the mere fact that rivers ran on Mars tells you it once had a thick enough sky and a warm enough surface to let them run. Mars had weather. Mars had a water cycle. Mars had a sky worth the name. Look at the low northern half of the planet, and the case gets stronger and stranger. Mars is a lopsided world. The southern hemisphere stands high and old and heavily cratered, while the entire northern third or so of the planet sits cumulus lower, a great smooth basin that wraps most of the way around. Many who study Mars think that basin, the vastas borealis, was once filled, that Mars had a genuine ocean spread across its northern lowlands, a shallow sea covering a third of the planet, while the southern highlands stood above it as dry land. Around the edges of that supposed shoreline there are features that look like the marks an ocean leaves, and the rivers of the southern highlands drain downhill toward it, exactly as rivers on a world with a sea would. Picture the planet not as it is, but as it may have been. A blue northern sea under an orange or pale sky, rivers running down out of the southern highlands to meet it, ice at the poles, cloud in the air. That is a world you could almost mistake from a distance for a young Earth. Now I have to be careful and honest, because this is one of the places where the science genuinely argues with itself, and I would rather show you the argument than sell you the tidy version. Whether Mars truly had a single great standing ocean, held for a long time, is not settled. The shoreline features are debated. Some of them do not sit at the level a real sea surface should, though there are ways to explain that with a wobble in the planet over time. And there is a colder reading of all the evidence, in which Mars was never a warm blue world at all but a frozen one, its water locked as ice most of the time, thawing only in bursts when a large impact or a spasm of volcanoes warmed things briefly, cutting the channels in short violent episodes rather than over long gentle ages. Under that reading, Mars was less an early Earth and more a cold desert that occasionally ran wet. The truth is probably somewhere in the argument, and we do not yet know where. But hold on to what survives the argument, because it is the load-bearing part and it does not depend on which side wins. Whether Mars held a long-lived ocean or a frozen sea that thawed in fits, Whether it was mild for ages or cold with warm interruptions, it had liquid water on its surface and a thick enough atmosphere to allow it. That is not in doubt. The rivers are there, the deltas are there, the lake basins are there, and a delta in particular is hard to fake because it takes standing water and a river feeding it over time to build one. The rock chemistry backs the shapes. Across the older terrain of Mars there are clays and other minerals that only form when rock sits in contact with liquid water for a long time, the mineral residue of a wet world, lying exactly where the ancient rivers and lakes were. You cannot make those minerals without water, and there they are. So the water is not merely inferred from the outline of a valley, it is recorded in the chemistry of the ground itself, and we can date it, roughly, by counting craters. A surface exposed for longer collects more impacts, so heavily cratered ground is old and smooth ground is young, and counting the craters on the wet terrain places the age of the rivers back around 3.5 to 4 billion years in the first stretch of the planet's life. There is even a genuine puzzle folded into that date, worth admitting because it shows how strange the early wet Mars really was. Back then the sun was noticeably dimmer than it is now, only about 70% as bright, because a young star of the sun's kind burns fainter before it slowly brightens with age. A dimmer sun should have left early Mars colder than it is even today, far too cold for any liquid water, and yet the water plainly ran. How a world further out, under a fainter sun, stayed warm enough to keep rivers flowing is a real and unsolved question, usually answered by supposing a far thicker blanket of greenhouse gases in that early air, holding in what little warmth there was, which only sharpens the whole point. Early Mars needed a thick sky to stay warm and wet, and it had one, and then it lost it, and the losing of that sky is the entire death we are tracing. There is one more thing this wet early Mars raises, and it is the question tonight's title quietly asks, so let me face it plainly rather than dodge it. If early Mars had water and a real sky for hundreds of millions of years, then it had for that stretch roughly the conditions in which life began on Earth, which means Mars may once have been not just habitable, but inhabited, that life may have started there too, in some warm, wet crater lake, in the same early stretch it started here. We do not know. We have not found it. There is no confirmed trace of Martian life, past or present, and there may never have been any to find. But here is the honest and unsettling part. If life did begin on Mars, then the dead rusted desert we are standing on is not merely the corpse of a world. What died there was a living one, a place where the whole experiment may have run for a while and then been snuffed out, not by any disaster of its own making, but simply because the planet it lived on lost its heat and its air out from under it. That is the darker reading of Mars, and it is a real possibility, not a fantasy. Mars might be what a world looks like a few billion years after its life dies with it. And if that is what Mars is, then the mirror it holds up to Earth is even less comfortable than a bare dead rock, because it is a portrait of a living world outliving the very conditions that made it live. So the modest, unarguable version of early Mars is already enough for everything that follows. Early Mars was wet. Early Mars had a real sky. Early Mars, 4 billion years ago, was a world where the ingredients we associate with a living planet were present and in motion, and then it was not. That is the pivot the whole video turns on, so let me say it as plainly as I can. Two worlds formed side by side, out of the same cloud of dust and gas around the same young sun, at the same time, of much the same stuff. One of them, Earth, is still wet and blue and breathing 4 billion years later. The other, Mars, is the frozen, rusted desert we started on, its rivers dry, its sea gone, its sky stripped to 1/100th of what it needs. They started in the same place, they did not end in the same place. And the difference between them is not that one was blessed and the other cursed from birth. The difference, as we are about to see, is mostly a difference of size, and size buys time, and time is the only thing that separates a living world from the corpse of one. There is a temptation here to tell a comforting story, that Mars was simply the runt, too small and too far out to ever really make it. A failed world that never had much of a chance, unlike our own robust and favoured Earth. Resist that, because it is exactly the reassurance this video is built to take away. Mars did not fail at the start. Mars succeeded at the start. It did the hard part. It formed with water and air and warmth, and it held them for hundreds of millions of years, long enough to run rivers and fill a sea, long enough that if life ever gets going easily, it might well have got going there. The tragedy of Mars, if a planet can have one, is not that it never lived. The tragedy is that it did live, in the sense that matters for a world, and then the life support failed. And the thing that failed was not on the surface where all the drama is. It was deep down, at the center of the planet, in a part of Mars you can never see, running an engine that every rocky world depends on, and that not one of them can keep running forever. So we have our before and our after. Before, a wet Mars with rivers and quite possibly a sea, under a real sky, 4 billion years ago. After, the frozen desert of today, its water fossilized into dry channels and buried ice, its air blown down to almost nothing. Something took Mars from the first state to the second, and it was not a passing catastrophe, not a single bad day, not an impact or an explosion, because the change was too thorough and too permanent for that. Whatever killed Mars killed it slowly and completely, and it started from the inside. To understand it, we have to leave the surface entirely and go down, past the crust, past the rusted rock, into the deep interior of the planet, to the engine that ran Mars and then stopped. Because when that engine stopped, Mars lost the one thing that had been protecting everything on the surface, and it never got it back. Mars died from the inside out, and it died because it was small. That is the mechanism, stated flat, and everything about the dead surface we walked on traces back to it. So let me take you down into the planet, because the thing that killed Mars is not visible from orbit and never was. It happened at the center. Start with what a rocky planet actually is, because most people carry the wrong picture. We think of a planet as a solid ball, an inert lump of rock hanging in space. It is not. A young rocky world is a heat engine, and it runs on the heat left over from its own violent birth, plus the warmth of radioactive elements decaying deep inside it. At the center of a world like Mars or Earth sits a core of iron and nickel, and while that core is hot enough, the metal in its outer part is liquid, and it moves. It churns, slowly, in great convecting currents, hot metal rising and cooler metal sinking, turning over and over across millions of years. A moving liquid metal, electrically conducting metal in motion, does something striking. It generates a magnetic field, not a small one, a single global field that wraps around the entire planet, reaching far out into space on every side. This is what physicists call a dynamo, and it is the beating heart of a living world. You cannot see it, it does no obvious work on the surface, and it is the only reason the surface has an atmosphere at all, as we are about to find out. Now here is where size becomes destiny. Mars is small. It is only about half the diameter of Earth, and because volume falls away so fast as you shrink a ball, Mars has only a bit more than a tenth of Earth's mass, roughly a ninth. That sounds like a modest difference. It is not modest at all, because of how heat works. A planet holds its heat in its volume, in the whole three-dimensional bulk of it, but it loses that heat only through its surface, the two-dimensional skin on the outside. Shrink a world and its volume falls away much faster than its surface area, so a small world has proportionally far more skin for its bulk, and it bleeds its internal heat into space far faster than a large one. A small planet is like a small cup of coffee next to a large pot. Both start hot. The little cup goes cold while the pot is still steaming, not because it was ever hotter or colder to begin with, but simply because it is small, and small things lose their heat fast. Mars is the little cup, Earth is the pot. So Mars cooled quickly. Within its first several 100 million years, the heat that drove the churning of its core ran down. The liquid metal at the center slowed and stilled, and the convecting currents that had generated the global magnetic field faltered and stopped. The dynamo switched off, and when the dynamo switched off, the great magnetic field that had wrapped around the whole of Mars collapsed, and for all practical purposes vanished. The planet that had been shielded was now bare. We are not guessing about this, and this is one of the places where Mars kept the receipt, out on its surface, where the camera can stay. When certain rocks form and cool in the presence of a magnetic field, they lock in a record of that field, like a compass frozen at the moment the rock hardened. Across the ancient southern highlands of Mars, the oldest terrain on the planet, the rock is strongly magnetized in banded stripes, a clear fossil imprint of a powerful global field that existed when those highlands formed. But the younger ground, including the Great Basins blasted out by giant impacts early in Martian history, carries almost no such magnetism. The field was there when the old highlands hardened, and it was gone by the time the younger surfaces formed. The rock itself has time-stamped the death of the dynamo. Mars had a magnetic heart, and then, early in its life, that heart stopped, and the rock remembers the exact era it happened. We found that fossil field almost by accident, when an orbiting spacecraft mapping the planet picked up the banded magnetism locked into the southern crust, stripe after stripe of it, a pattern that could only have been laid down while a strong global field was present. And the youngest, largest scars on Mars pin the timing from the other side. The giant impact basins, the huge circular wounds where early collisions punched deep into the planet, carry almost no magnetism of their own, which means that by the time those basins were blasted out, the field was already gone. So the field was on when the old highlands hardened and off by the time the Great Basins formed. And that brackets the death of the dynamo to early in Martian history, within roughly the first several 100 million years. The heat that had run it came from two sources, both finite. There was the primordial heat, the leftover warmth of the planet's violent birth, when countless collisions and the sinking of iron to the center had left the whole world molten. And there was the slow heat of radioactive elements decaying deep inside, a trickle of warmth released atom by atom across ages. A large world banks a great deal of both and doles it out slowly. A small world like Mars had less of each to begin with and spent it fast, and once it was spent there was nothing bringing more, and the engine at the center simply went cold. It is worth seeing, by contrast, why Earth's engine has lasted so much longer, because it is not only a matter of raw size. At the very center of the Earth the core has begun to freeze, a solid ball of iron growing slowly at the heart of the liquid outer core, and the act of freezing itself releases heat and stirs the liquid metal around it, helping to drive the churning that makes the field. So Earth has a second, slower source of energy for its dynamo that a small, fast cooling world never gets to tap, the steady crystallizing of its inner core across billions of years. That is part of why Earth's field has held for 4 billion years and shows no sign of failing soon. But read the fine print. That inner core grows only because the Earth is slowly cooling. The very process feeding the dynamo is itself a form of the planet running down. Earth's engine lasts longer than Mars's did, but it lasts longer by drawing on the same finite bank of heat, only more cleverly and more slowly. The direction is identical. Earth is simply further from the bottom of the account. I should mark the honest edge, because the precise story is still being sharpened. Exactly when the Martian dynamo died, and exactly why it died when it did, is a live area of study, with estimates spread across a few 100 million years and several competing explanations for what finally stilled the core. Some of the detail may yet change, but the shape of it is not in doubt and is well supported from several directions. Mars had a global magnetic field early on, generated by a churning core, and it lost that field early, and it lost it because a small world cannot keep its core hot and turning for long. The engine ran, and then the engine stopped, and it stopped because Mars did not have the mass to keep it going. That is the settled part, and it is the part that kills the planet. Because here is the thing about that invisible magnetic field, the thing that makes its loss the pivot of the whole story rather than some abstract fact about the core. That field was not decoration. It was a shield. While it stood, it wrapped the entire planet in an invisible barrier that deflected the constant stream of charged particles pouring out of the sun, turning them aside before they could reach the atmosphere, the way a boulder in a river splits the current and sends it around. The air of Mars sat safe inside that shield. The rivers ran under its protection, and the moment the dynamo died and the shield came down, nothing was turning that stream aside anymore. The atmosphere of Mars, the thick sky that had held the rivers and the sea, was now standing fully exposed to the direct blast of its own star, with no protection at all, for the first time since the planet formed. Think about what that means for the thin tan arc of air we looked at on the edge of the Martian disk. While the shield stood, that arc was thick and full, a proper atmosphere. The instant the shield fell, that arc was living on borrowed time, exposed, undefended, with the sun beginning to work at it. It would not vanish in a day, but from the moment the dynamo died, the sky of Mars was doomed, and the only question was how long the stripping would take. A planet had lost its heart, and losing its heart meant losing its shield, and losing its shield meant losing its air, and losing its air meant losing everything the air made possible, the water, the weather, the whole living surface. All of it followed, in order, from a small core going cold at the center of a small world. So we have moved the death back one more step, from the surface to the shield to the core, and the core is where it truly starts. Mars was too small to keep its engine running. The engine stopped, the shield fell. That is the cause. But we have not yet watched the actual killing, the part where the air is taken and the water is lost. For that we have to follow what happened next. Once the shield was down and the sun had a clear shot at an undefended world, we have to watch a star strip a planet. And the star did not do it with heat or with a single blow. It did it slowly, particle by particle, over an unimaginable stretch of time. And the process is still going on today, gently, on what little of the Martian sky is left. Once the shield was down, the sun took the sky of Mars apart molecule by molecule, and it is still doing it today. The sun did not roast Mars, and it did not blow the air off in one great gust. What it did was quieter and more relentless than that, and understanding it is the key to understanding how a living world dies. So let me show you exactly what happens when a star meets a planet that has lost its guard. The sun does more than pour out light and warmth. It also blows constantly and in every direction, a thin stream of charged particles called the solar wind, fragments of atoms traveling out from the sun at hundreds of kilometers a second. This wind never stops and it fills the whole solar system. Every planet stands in it. On a world with a magnetic shield, the wind is deflected, split and swept around the planet, and the atmosphere sits safe in the sheltered pocket behind the shield. But Mars, after its dynamo died, had no shield. So the solar wind arrived at the top of the Martian atmosphere and hit it directly, at full speed, with nothing in the way. When a fast-charged particle from the sun slams into the upper atmosphere, it knocks gas molecules loose and flings them out into space, a little like a sandblaster stripping paint off a wall one grain at a time. Physicists call this sputtering, and it is not a dramatic process to watch. What it comes to is the slow, steady erosion of a planet's air. One molecule here, one molecule there, endlessly, for as long as the wind blows and the shield is down. There are other loss processes working alongside it. The light gases simply drifting off the top, chemistry breaking molecules apart so their pieces can escape. But the through line is the same. With nothing to turn the solar wind aside, the atmosphere of Mars was exposed at the top to a stream that carried it off into space, thinning it century by century, and the pressure at the surface fell and kept falling. We are not reconstructing this only from theory. There is a spacecraft in orbit around Mars right now, built precisely to measure this, and it watches the solar wind stripping gas off the top of the Martian atmosphere in real time, today, billions of years after the worst of it. The stripping has slowed now that there is so little left to take, but it has not stopped. Mars is still very slowly losing what remains of its sky to the sun, and we can measure the leak. The numbers, read straight from orbit, are small in any one moment and merciless over time. The stripping today carries off something on the order of a few kilograms of atmosphere every second, gas by gas. And when a storm erupts on the sun and the solar wind gusts harder, that rate can jump several times over for as long as the gust lasts. A few kilograms a second sounds like nothing set against the whole sky of a planet, and across a human lifetime it is nothing. But run it across hundreds of millions of years and add in the far faster stripping of the distant past, when the young sun was more violent and the shield was already down, and it adds up to most of an atmosphere carried off into space. The pressure at the surface fell and kept falling, and every drop in pressure narrowed the range of places and seasons where water could still be liquid, until that range closed to almost nothing. Picture the same patch of Martian ground across the whole span. Early on, a shoreline under a real sky, water at the edge, weather overhead. Then, as the pressure sank, the water retreating, the last shallow pools freezing and evaporating, the shore drying to cracked mud, the mud to dust. Then only the dust, and the thin cold wind, and the dry channel where a river had run, under a sky steadily emptying toward the tan ghost it is now. Not a catastrophe, a slow and total draining, metered out over a stretch of time longer than there has been complex life on Earth. To feel the scale of what was taken, put numbers on the sky itself. Early Mars very likely carried an atmosphere at least a fair fraction as thick as Earth's, plenty to warm the surface and hold liquid water, and today it stands at roughly 6/1000ths of Earth's pressure. That is the measure of the theft. Not a trimming, not a halving, but the removal of almost the entire sky, better than 99 parts in 100, carried off grain by grain until only a rusty trace remained. And this is the place to turn the camera back toward our own world for a moment, without landing on it. The air you are breathing, the whole weight of atmosphere over your head that lets water sit in a glass without boiling, that shields you from the raw solar wind, that holds the warmth of the day into the night, is exactly the thing Mars had and lost. It is not a fixed feature of a planet. Air is a thing a world holds only for as long as it can defend it, and Mars is the proof, hanging in our own sky, of what is left when a world can no longer keep its air. What happened to Mars is not a Martian peculiarity. The same thing happens to the sky of any rocky world that loses its shield, and Earth's sky sits behind the same kind of shield, holding for now, and the air that survives carries a fingerprint of the loss. In the thin Martian atmosphere, the water that is left is unusually rich in a heavy form of hydrogen called deuterium. That matters, because ordinary light hydrogen escapes to space more easily than the heavy kind, so a world that has lost most of its water to space ends up enriched in the heavy version that got left behind. Mars is heavily enriched. The very chemistry of its remaining air is a signed confession that oceans of water once escaped from the top of its atmosphere into space. So follow the water, because the water is what we care about. As the air thinned and the pressure dropped, liquid water on the surface became impossible. Below a certain air pressure, liquid water cannot exist in the open at all. It either freezes or it boils away into vapor, even in the cold. And that vapor rises, and up at the top of the atmosphere, sunlight breaks the water molecules apart, and the hydrogen escapes to space. And once the hydrogen is gone, the water can never reassemble. So the rivers did not simply freeze and wait. Some of the water froze into the ground and the poles, where a great deal of it still sits as buried ice. But a large share of it was lost for good, broken up and bled off into space along with the air, gone in the same slow leak that took the sky. The lakes drained or froze or evaporated. The northern sea, if there was one, retreated and vanished. And what was left was the dry, rusted desert we started on. Its water either locked underground as ice or lost to the stars entirely, its air reduced to 1/100th of what it needs to run a river. I have to be careful and fair right here, because this is the exact spot where the popular version of the Mars story tends to overreach, and I promise not to do that. The simple version says, Mars lost its magnetic field, therefore the solar wind stripped its air, full stop, one clean cause and one clean effect. The real picture is messier, and the honest scientists are still working on it. The exact rate at which the field's loss mattered, and how much of the stripping was down to the missing shield versus other escape processes that work regardless, is genuinely debated. There are even models suggesting that a weak, patchy magnetic field can in some ways help air escape faster in places rather than protect it, by funneling the solar wind down onto the atmosphere along open field lines. So the tidy slogan overstates a clean certainty we do not have. But strip away the overstatement and the load-bearing sequence survives intact and is well supported. Mars had a thick atmosphere and surface water. It lost its global shield when its core cooled. Over the hundreds of millions of years that followed, its atmosphere was stripped to a fraction of what it had, and its water was frozen underground or lost to space. The sky and the sea of a living world were taken, and the sun did most of the taking. Now go back one more time to that thin arc of air on the edge of the Martian disk. because we have just watched it thin. When the shield stood, that arc was thick and full. Once the shield fell and the stripping began, the arc grew fainter, century by century, as the sky was carried off. And what you see today, that faint dusty tan smear hugging the rim of Mars, is the end state of that thinning. It is not a healthy atmosphere caught in a thin moment. What you are seeing is the leftover, the final 100th, the receipt for an entire sky that the sun carried away after the planet lost the ability to defend it. Every time you see that thin tan line on the edge of Mars, you are looking at how much air is left after 4 billion years of a star eating an undefended world. Almost none. And that raises the question this whole section has been driving toward, the one that should be starting to feel personal. If the thing that killed Mars was the loss of its magnetic shield, and the shield fell because the core cooled and the core cooled because Mars was small, then what about a world that is not small? A world with a core still hot and a shield still up? What about Earth, which still has its magnetic field intact, still deflecting that same solar wind today? Does having the shield mean Earth is safe? Does it mean we are exempt from Mars's fate, standing behind a guard that Mars lost? It is the obvious hope to reach for, and I am going to answer it directly. But before I turn the camera on Earth, I want to show you one more world, because Mars is not even the end of this road. There is a place that took the same process further, a world that lost not just its sea and most of its sky, but very nearly everything. And it has been sitting still, finished, for so long that it shows us exactly what the far end of this looks like. There is a world even more finished than Mars, and it is the nearest one to us. Look at the moon, not as scenery, not as the familiar face in the night, but as what it actually is, which is a planet-sized rocky body that ran all the way down to the end of this same road and then stopped, and has been sitting at the end of it, unchanged, for billions of years. If Mars shows you a world in the late stages of dying, the moon shows you a world that finished dying so long ago that nothing has happened to it since. It is the clearest picture we have of the final state, and the final state is not violence but stillness. The moon is smaller than Mars, much smaller, only about a quarter of Earth's diameter, and it started with far less water and air than Mars ever had, so it ran through the whole process faster and more completely. Today the moon has effectively no atmosphere at all, not a thin one like Mars, but essentially none, a vacuum so nearly total that the few stray atoms above the surface barely deserve the name of air. And it has no global magnetic field, no dynamo running at its core, no shield of any kind. Stand on the moon in full daylight and the sky directly overhead is not blue and not tan, but black, pure black, with the sun blazing in it as a white disk and the stars still there behind it if your eyes were shielded from the glare, because there is no air to scatter the light into a sky. Noon on the moon has a black sky. That is what a world with no atmosphere looks like from the ground. The day is simply the airless dark with a sun hanging in it. And with no air to move the heat around or hold it in, the temperature on the moon does something Earth never does. In direct sunlight, the surface climbs well past 100 degrees Celsius, and a few steps away in permanent shadow, or through the long lunar night, it falls to more than 150 degrees below zero. There is no air to carry warmth from the hot places to the cold ones, no blanket to blunt the day or hold the night, so the two extremes sit side by side with almost nothing between them, blazing light and killing cold, separated by the width of a shadow. And here is a detail that ties the moon back into the whole story rather than leaving it a special case. The moon, small as it is, seems once to have had a churning core and a magnetic field of its own early and briefly, before it cooled and stilled. Rocks brought back from the surface carry a faint fossil magnetism, the moon's own version of the record written into the Martian highlands. So even the moon in its way ran the same engine for a little while and lost it, faster and earlier than anyone, because it was smaller than anyone. What is left now is a surface slowly ground to powder by the endless rain of micrometeorites, impacts too small to leave a visible crater but numerous enough to churn the top layer into fine grey dust over billions of years, the patient last erosion of a world with nothing else happening to it at all. The moon even shows us its stillness by always showing us the same face. It turns exactly once for every circuit it makes of the Earth, so one side stays fixed toward us and the other, the far side, was never seen at all until we sent machines around the back of it. And it too is the same ancient cratered rock, if anything older and more battered, untouched by wind or water for billions of years. A world that holds one frozen expression turned toward its neighbour for the whole of recorded history is a fair emblem of what finished means. Now set that beside the Earth. Our surface is the opposite of the moon's in every way that counts. It is young almost everywhere, constantly wiped clean and laid down fresh, so that most of the original face of the Earth, the record of its first billion years, has been erased entirely by the churn of a living world. The moon has kept everything and changed nothing. Earth has changed everything and kept almost nothing. And the reason for the difference is heat, the same heat we keep returning to. The moon is what Earth would look like if you switched the engine off and let the restlessness drain away. Every scar preserved, every process halted, one face turned forever toward the dark. And then there is the surface, which is the part that tells the real story. The face of the moon is covered in craters, and the craters are piled on top of craters, overlapping, layered, some of them nearly as old as the moon itself, more than 4 billion years old. Every one of those craters is a scar from an impact, and the striking thing, the thing that should stop you, is that they are all still there. Almost nothing has erased them. On Earth, a crater that old would have vanished long ago, worn away by rain and wind, buried under sediment, swallowed by the slow churn of the crust, overgrown, rewritten. Earth heals its scars, the moon does not. There is no wind to wear the craters down because there is no air. There is no water to erode them. There is no shifting crust to swallow them. Nothing moves. So every impact the moon has ever taken is still written on its face, a 4 billion year old record with nothing painted over. The moon keeps every scar it is ever given because it has no way left to heal. That is the deepest thing the moon has to teach, and it is worth saying slowly because it flips how we usually think about a dead world. We imagine death on the scale of a planet as something dramatic, a world blasted or burning or torn apart. But that is not what a finished world is. A finished world is one where nothing happens anymore. A living world is restless. It moves its crust, it runs its water, it turns its air. It constantly repaves and reworks its own surface, erasing the old and laying down the new. All that restlessness is the outward sign of an engine still running inside. When the engine stops, the restlessness stops, and the world goes still, and it holds whatever shape it had at the moment it died, forever, because there is nothing left to change it. Stillness is death at the scale of worlds. The moon is not violent, the moon is simply, permanently at rest. And it has been at rest, holding its craters unchanged for a span so long that the entire history of complex life on Earth would fit into a small corner of it. I should be fair about the comparison, because the moon and Mars did not die by exactly the same route. The moon is so small and started so dry that it never really had the wet, thick-skied phase Mars had. It was closer to finished from the beginning. So I am not showing you the moon as a mechanical twin of Mars, a world that ran the identical process one step further. I am showing it to you as the picture of the end state itself, whatever road a world takes to get there. Small worlds, airless worlds, worlds whose engines have stopped, all converge on the same final condition, and the moon is the nearest and clearest example of it. It is what any of these worlds looks like once the process is truly complete. No air, no field, no water, no change, just cratered rock under a black sky, keeping its scars going nowhere, for longer than we can hold in our heads. Now do the thing with the arc one more time, because the moon closes the sequence we have been building. Around Mars, that thin line of air on the edge of the disk was faint and tan, the last 1/100th of a lost sky. Look at the edge of the moon against the black of space and there is no line at all, none. The rock simply ends, sharp against the dark, a hard clean edge with nothing above it. No glow, no haze, no arc, no atmosphere to catch the sunlight sideways. Where Mars has a thin ghost of a sky, the moon has nothing whatsoever. That hard black edge, that total absence of any arc of air, is the visual endpoint of everything this video is about. It is what the rim of a world looks like when the atmosphere is not thinning but gone, completely and permanently. The thinning we watched on Mars has, on the Moon, reached zero. So now we have the whole grim sequence laid out in real worlds. A wet living Mars, 4 billion years ago, with a full sky. The stripped Mars of today, with its thin tan remnant. And the Moon, with no arc at all, the process run to completion. It is a spectrum of death, and every stage of it is a real place you can point a telescope at right now, which makes the obvious question impossible to avoid any longer. The one I have been holding off since we watched the Sun strip Mars. Every world we have looked at is dead or dying or finished. Mars is a corpse. The Moon is a corpse so old it has stopped decaying, and they are our neighbours, made of the same stuff, formed at the same time, standing in the same sunlight. So why out of all of them is Earth still alive? Why is our world still wet, still blue, still breathing, when the worlds on either side of it have gone silent? What is Earth doing that Mars and the Moon could not? The answer is simpler and more precarious than you might hope, and it is the hinge on which this whole video turns. Earth is still alive for one reason, and it is almost embarrassingly simple. Earth is bigger. That is very nearly the whole answer, and once you see it, the comfortable idea that our world is a fundamentally different and safer kind of place falls apart in your hands. Go back to the coffee analogy because it is exact. Mars was the small cup that went cold while the large pot was still steaming. Earth is the pot. Earth has about 9 times the mass of Mars and roughly twice the diameter, and that extra size means two things that together keep our world alive. It means Earth started with far more internal heat, and it means Earth loses that heat far more slowly, because a larger world has proportionally less surface for its bulk, and so bleeds its warmth into space at a gentler rate. So 4 billion years after both worlds formed, Mars has gone cold at the center while Earth's core is still fiercely hot, hot enough that its outer part is still liquid metal, and that liquid metal is still churning, still turning over in great slow convecting currents exactly as Mars's once did. Earth's dynamo is still running, Earth's core is still turning, and because the core is still turning, everything downstream of it still holds. Follow the chain, because it is the same chain we watch break on Mars, running here in the other direction, intact. Earth's core still churns, so Earth still generates a global magnetic field. That field still wraps the entire planet in an invisible shield, reaching tens of thousands of kilometers out into space on the side facing the Sun, and streaming out into a long tail on the side facing away. That shield still meets the solar wind and still splits it and sweeps it around the planet, exactly as Mars's shield once did, so the solar wind never reaches our atmosphere directly. And because the atmosphere is protected, it stays. The air is not being stripped off the top. The water is not being bled into space. The whole living surface, the oceans and the weather and the sky, sits safe in the sheltered pocket behind a shield that is still standing because, 4 billion years on, the engine that powers it has not yet run down. That is the difference between Earth and Mars. Not virtue, not luck at birth, not some special status, just heat and the size that holds onto it. You can even see the shield working if you know where to look, and it keeps the camera off the ground and out where it belongs, near the poles, where the field lines dip down toward the surface. Some of the solar wind does get funneled in along them, and where those charged particles crash into the upper atmosphere, they make it glow in curtains of green and red light, the aurora. Those shifting lights are not decoration. They are the visible flash of the shield catching the solar wind, the exact battle Mars lost, being fought and won over Earth's poles every single night. Every aurora is a small proof that the guard is still up. Mars has no aurora of that kind anymore, because Mars has no global shield to catch anything. On Earth, the lights are still on. The running core does more than hold up the shield, and this second gift matters just as much, and it will matter again when we come to how Earth dies. Because Earth is still hot inside, its surface is not fixed. The crust is broken into great plates that slowly move, dragged and shoved by the churning heat below, colliding and diving under one another and pulling apart, so that the whole face of the planet is constantly being remade. That restless resurfacing, which Mars and the Moon long ago lost, drives a slow chemical cycle that has quietly kept Earth livable for billions of years. As the planet warms, rock weathers faster and pulls carbon dioxide out of the air, which cools it back down. As it cools, that drawdown slows and volcanoes return carbon dioxide to the air, which warms it again. It is a thermostat run by the moving crust and the heat beneath it, and it has held Earth's temperature inside the narrow band where oceans can exist through all the changes of 4 billion years, including through the slow brightening of the sun so far. That thermostat is a large part of why Earth is still blue while its neighbours are dead. Hold on to it, because it is not only Earth's saviour. When we come to how the sun finally kills this world, it is the failure of exactly this thermostat, pushed past what it can absorb, that opens the door. The same system that has kept Earth alive is the one that gives out first. And the shield itself, for all its strength, is not the fixed thing we tend to imagine. Earth's magnetic field wanders and weakens, and every so often across the ages flips entirely, north and south, trading places over a few thousand years, the record of these reversals frozen into the rocks of the ocean floor in stripe after stripe, much as the fossil field is frozen into the crust of Mars. Through all of that, the field has stayed fundamentally strong, because the dynamo beneath it has kept turning. But it is a reminder that the shield is a living, changing thing that depends entirely on the churning below. Not a solid wall bolted permanently around the planet. It holds because the engine runs. And when the engine finally winds down ages from now, the field will not merely flip and recover as it always has before. It will fade and fail and stay failed, and the slow stripping of our own sky will begin. The shield is strong tonight. It will not outlast the heat that drives it. And now the touchstone, because this is the moment it turns from the dead worlds to us. We have watched the arc of air on the edge of a world thin and vanish, tan and faint on Mars, absent entirely on the Moon. Turn now to Earth, seen edge on from orbit, and look at its rim against the black. There is an arc there, and it is not a faint tan smear, and it is not missing. Instead, it is a clean, bright blue line, hugging the whole curve of the planet, vivid against the dark. That blue arc is Earth's atmosphere seen from the side, thick and full and healthy. The sky that Mars lost and the Moon never had. It is the single most alive thing you can see from space. When you look at that thin blue line wrapped around the Earth, you are looking at the living sign itself, the visible mark of a world whose engine is still running, whose shield is still up, whose air is still held. Every dead world we have looked at has lost that line or never had it. Earth still wears it. That blue arc is the difference between a living world and a corpse, drawn as a single line of light on the edge of the planet. But here is where I have to take the comfort away again, because the way I have told this so far, it sounds like good news, and it is not good news. This is a stay of execution, and a stay is not a pardon. Everything keeping Earth alive, the whole chain from the hot core to the running dynamo to the standing shield to the held atmosphere to that bright blue arc, depends on one thing, and that one thing is finite. It depends on leftover heat. Earth is alive because it is still warm inside, and it is still warm inside because it is big enough to have held on to the heat of its birth for 4 billion years. But 4 billion years is not forever. The heat that runs Earth's core is not being replenished from anywhere. All of it is the banked warmth of the planet's violent formation, plus a dwindling contribution from radioactive decay, and it is slowly running down. Earth is a larger cup of coffee than Mars. It is not a bottomless one. Earth is cooling too, just far more slowly, and one day further off than Mars's death, but no less certain, our core will cool enough that its dynamo falters, exactly as Mars's did. So the only honest way to say why Earth is still alive is this. Earth is not a different kind of world from Mars, but the same kind of world, running the same process, on a longer clock. Earth is earlier in the story, not exempt from it. The blue arc is the living sign, yes, but the living sign is temporary, because the heat that holds it up is temporary. Mars is what Earth looks like when the heat runs out, and that reframes the obvious question into a far more uncomfortable one. It is not whether Earth is safe, because Earth is not safe, only early. The real question is when the heat runs low, what happens, and whether the cooling core is even the only clock we have to worry about. and it is not. Because while the core cools slowly across billions of years, there is a second process already underway, one that has nothing to do with Earth's insides at all, one that comes not from below but from above, from the sun itself. There are two clocks running on Earth, not one, and they are counting down to the same ending by different routes. This is the turn the whole video has been climbing toward, so let me put both clocks in front of you at once. Earth has two clocks running on it, and both of them end at a dead world. That is the turn, and it is the moment the safe distance between us and Mars collapses. Up to now you could watch Mars die of causes that felt safely foreign. A small planet with a cold core, a lost shield, a stripped sky. Nothing to do with our big warm living world. That comfort ends here, because Earth is not running down one clock toward its ending. There are two of them running at once, by two completely different routes, and neither of them is anything we did, and neither of them is anything we can stop. The first clock is the one we just uncovered, the cooling core. Earth's engine is running now, but it is winding down, and one day, on the order of 2 to 3 billion years from now, the core will have cooled enough that the churning slows and the dynamo falters, exactly as it did on Mars. When that happens, Earth's global magnetic field will weaken and decay, and the shield that has protected our atmosphere for 4 billion years will start to come down. And once the shield is down, the same solar wind that stripped Mars will begin to strip Earth. The same process, the same star doing the same slow taking. It is the Mars death, and Earth is genuinely on that road, just with more heat in the tank, and so further from the end of it. That clock reads a couple of billion years, give or take, before it even begins in earnest, which is so far off it can feel like no threat at all. But it is running, and it runs in only one direction, and there is no winding it back up. That would be enough on its own. But there is a second clock, and it is faster, and it does not come from inside the planet at all. It comes from the sun. And this is the part that catches people off guard, because we think of the sun as the steady, reliable thing in the sky, the one fixed point, the source of all our warmth and safety. But the sun is not steady on the long view. The sun is slowly getting brighter. As it fuses hydrogen into helium in its core, the helium builds up, the core grows denser and hotter, and the sun burns a little more fiercely as the ages pass. The rate is about 10% brighter every billion years. The reason the sun brightens is buried in how it burns. Deep in its core it is fusing hydrogen into helium, and as the ages pass the helium ash builds up at the center, making the core denser and hotter, which makes the fusion run faster and the whole star shine brighter. This is not a phase or a fluke, but the ordinary aging of a star of the sun's kind, and it has been underway since the sun was born. Our sun is already about a third brighter than it was when the Earth formed, and it will keep climbing at that same steady pace for billions of years to come. So the warming that will one day boil the oceans is not something that switches on in the far future. It carries on a brightening that has run the entire time life has existed on Earth, held at bay so far only by that carbon thermostat quietly pulling the carbon dioxide down to compensate. But the thermostat has a flaw. It can only draw carbon dioxide so low before there is too little left for plants to breathe and the compensation fails. Once the sun brightens past the point the thermostat can offset, the temperature is free to climb, past anything in Earth's history, past what complex life can bear, and then past what the oceans can bear, and none of it requires a single thing to go wrong. It is only a star aging exactly as stars do, over a planet that cannot step out of the way. And notice the cruel independence of the two clocks, because it is what makes the trap complete. If Earth's only trouble were its cooling core, you could at least tell yourself the end was billions of years off, further even than Mars's death lies in the past. And if the only trouble were the brightening sun, you could imagine, in some far-fetched way, moving the planet to stay ahead of it. But there are two, and they are unrelated, and dealing with either one does nothing to the other. Cool the sun somehow and the core still fails. Reheat the core somehow and the sun still boils the seas. They share no cause and they share no cure. One is a fact about the size of the Earth, and the other a fact about the age of the sun, and a living world simply happens to sit downstream of both. The oceans are the first to go, on the sun's schedule, in a heat that needs no help from us and cannot be talked out of arriving. Everything after that is only the long working out of a sentence already past. It helps to set that billion years against something real out among the worlds, because a billion years is a number the mind slides straight off. Consider that the entire history of animal life on Earth, everything from the first crawling things in the ancient seas up to now, has taken well under a billion years. So the time Earth has left before the sun begins to boil its oceans is comparable to the whole span in which complex life has existed at all. We are not near the end of a long afternoon. We are somewhere around the middle of the only day this world gets, or set it against Mars directly. Mars has been dead and stripped and rusted for something like 4 billion years already, nearly the age of the solar system itself. It died young and has been a corpse for almost the entire life of the sun. Earth, if it holds a livable surface for another billion years and then lingers billions more as a slowly dying rock, will still in the end spend far more of its existence dead than alive, exactly as Mars has. That is the ordinary balance for a rocky world. A relatively brief lit stretch, and then a long darkness on either side of it. The living phase is the short part, and the sun that grants that phase has its own clock running over the top of both of ours. It has burned for about 4.5 billion years and has something like 5 billion left before it swells into a red giant and ends the inner solar system for good. So even the star we are counting down against is itself counting down, and everything, the core, the shield, the oceans, the sun, is running the same way at once toward cold and dark and done, each on its own scale. The one strange and precious thing in the whole arrangement is that, for this single stretch, on this single world, it is all still running the right way. That sounds gentle, and on any human scale it is nothing at all, undetectable across a whole civilization. But a planet does not live on a human scale. A planet lives on the scale where 10% every billion years is a rising flame under a pot, and the pot is the Earth, and the thing in the pot is the ocean. Here is what that rising brightness does, and it does not need Earth's core to fail at all. In roughly a billion years, the sun will be bright enough that the delicate balance keeping our world temperate breaks. Earth has a natural thermostat, a slow cycle that pulls carbon dioxide out of the air as the planet warms and so lets it cool itself, and that thermostat has held our climate livable for billions of years. But as the sun brightens, that thermostat is forced to pull carbon dioxide down and down to keep fighting the heat until it hits a floor, until there is so little carbon dioxide left that plants can no longer photosynthesize and the base of the living world starts to fail. And past that point the heat keeps climbing, and the oceans begin to evaporate in earnest. And here the process turns vicious, because water vapor is itself a powerful trapper of heat. More heat lifts more water vapor into the air, and more water vapor traps more heat, and that traps still more, and the whole thing runs away. The oceans rise into the sky as vapor, and up at the top of the atmosphere sunlight breaks those water molecules apart, and the hydrogen escapes to space, exactly as it did on Mars, exactly as the deuterium fingerprint records. The water does not just evaporate, it leaves the planet, and a world that has boiled its oceans into the sky and lost them to space is not a world with a heat problem. What it becomes is a world with no water at all, permanently, on a timescale of about 1 billion years, from the sun alone, with Earth's core still warm and its shield still up the whole time. So look at what we have. One clock runs in the core, slow, a couple of billion years off, and it ends by taking the shield and letting the sun strip the air, the pure Mars death. The other clock runs in the sun, faster, about 1 billion years, and it ends by boiling the oceans into space, a death Mars did not quite have but a nearby world did, as we are about to see. 2 clocks, one in the ground, one in the sky, one takes the air, the other takes the water, and they are both running right now, both counting down, both pointed at the same finish, which is a dry, stripped, lifeless rock where a living world used to be. The blue arc of air on Earth's limb, that bright living line we just turned to with such relief, is not a permanent feature of our world. That bright line is a reading on 2 timers, and both timers are moving, and the arc is exactly the thing they are counting down to erase. That is the floor dropping out, and I want to let it drop rather than soften it. For most of this video, Mars has been the cautionary tale, the other world, the one it happened to. And what these two clocks tell you is that it is not the other world but the same world ahead of us on the road, showing us the destination. Earth is not exempt. Earth is early. Everything that took Mars is either already scheduled for Earth or has a direct equivalent already scheduled, and the scheduling has nothing to do with our smokestacks or our choices or our behavior. It is written into the size of our core and the aging of our star, and there is no version of good behavior that unwrites it. This is the spike of the whole thing, the point where the distance between Earth and Mars stops being billions of kilometers of space and becomes instead only a stretch of time, a stretch that is already elapsing. There is a question I have been circling and have not answered yet, and it decides what our own ending actually looks like. Does Earth finish cold and dry and stripped bare the way Mars did? Or does it finish scorched, drowned in its own heat? The answer is stranger than either, and I promise I will get to it. But first I have to show you a second world that died, one that took the other road entirely. There is a second world that boiled its oceans into the sky, and it is not far away, and it is almost exactly Earth's size. Venus. If Mars shows you the cold death, the stripping of a small world that lost its heart, Venus shows you the hot death, the runaway that a world can suffer when the heat wins, and it is the death the brightening sun is steering Earth toward first. So before we settle which ending is ours, let me take you to the one planet that has already been through the fire. Start with how alike Venus and Earth are, because that is what makes it frightening rather than exotic. Venus is almost our twin. It is just a touch smaller than Earth, with about 80% of our mass made of the same kind of rock, formed in the same part of the same disk around the same sun. If you were sorting the young planets into groups, you would have put Venus and Earth together without hesitation. Two sister worlds of nearly the same size sitting next to each other in the warm inner solar system. And there is good reason to think Venus began wet, that it formed with a similar share of water to Earth, enough to have had oceans on its surface early on. Two sister worlds, both with water, both the right size, side by side. And today one of them is the living blue planet you are standing on, and the other is the single most hostile world in the solar system. Because Venus now is hell, and I mean that as a plain description, not a flourish. The surface temperature on Venus is about 460 degrees Celsius, hot enough to melt lead, hotter than a kitchen oven can go, and it is that hot everywhere, at the poles as much as the equator, on the night side as much as the day, because the atmosphere is so thick it smothers the whole planet in even, unrelenting heat. And the atmosphere is crushing. The air on Venus presses down at the surface more than 90 times as hard as Earth's does, a weight equivalent to being nearly a kilometer deep in the ocean, enough to flatten most spacecraft we have ever landed there within an hour or two. That air is almost entirely carbon dioxide, and high above the surface it is wrapped in thick, unbroken clouds, not of water, but of sulfuric acid. A world the size of Earth, that likely started with oceans, is now a lead-melting, spacecraft-crushing, acid-wrapped furnace. The question that matters for us is not how strange that is, but how a world so like Earth became it. The answer is the runaway greenhouse. And it is the same vicious feedback we just saw beginning on Earth's own second clock, except that on Venus it already ran all the way to the end. Venus sits closer to the sun than we do, so it received more sunlight from the start, and early on that was enough to keep its water as vapor in the air rather than letting it settle into stable, cool oceans. And water vapor, remember, traps heat, so the warmth lifted more water into the air, and the water vapor trapped more heat, and that lifted still more water, and the temperature climbed and climbed in a spiral that fed itself. The oceans, if they were ever fully there, boiled away into the sky, and once all that water was up in the atmosphere, sunlight high above split the water molecules apart, and the light hydrogen escaped to space, permanently. Venus did not just get hot, it lost its water entirely, broken up and bled off into space, until there was nothing left to rain back down, and the planet was left dry and cooked with a thick blanket of carbon dioxide holding the heat in forever. And Venus kept the receipt, the same kind of chemical confession Mars left, in the traces of water vapor that remain in the Venusian atmosphere. The heavy form of hydrogen, deuterium, is enormously enriched, well over 100 times more concentrated relative to ordinary hydrogen than it is on Earth. That is the unmistakable signature of a world that once had a great deal of water and lost it to space, the light hydrogen escaping and leaving the heavy behind, just as on Mars, but far more extreme. The rocks and the air of Venus testify that this was once a wetter world, and that its water is now gone, broken apart and lost to the sky. And Venus adds a strange twist to the pattern we have been building, because it breaks a rule Mars seemed to teach us. Venus is almost exactly Earth's size, so by rights it should have kept a hot, churning core and a global shield, and yet it has essentially no global magnetic field at all. The likely reason is that Venus turns astonishingly slowly, taking longer to spin once on its axis than to circle the Sun, and a dynamo needs a decent rate of spin to organize the churning metal into a field. So here is a world that kept its heat and lost its shield anyway, for a different reason than Mars, which shows there is more than one road to an undefended planet. And unlike Earth, Venus has no system of moving plates steadily remaking its surface. It seems instead to bottle its internal heat and release it in great planet-wide spasms, its whole face apparently repaved by volcanism a few 100 million years ago in a single catastrophic resurfacing, rather than the gentle recycling Earth manages. We have tried to land on it, and the surface answered plainly. The probes that reached the ground survived barely an hour or two before the heat and the crushing pressure killed them, sending back a few images of a dim, baking, rock-strewn plain under an orange sky before they went silent. That is the fire ending as a real place you can photograph, for the hour or so a machine can last on it. And the crucial difference from Mars is worth holding clearly. Mars lost its air and kept a trace of its water frozen underground. Venus kept its thick air and lost its water utterly to space. Two opposite balances, both of them fatal, and Earth we are about to see is on course to suffer them in turn. Sit with how close a call Venus really is, because that is the part that should unsettle you most. Venus is not far away, and it is not much smaller than Earth. It sits just inside our own orbit, nearer the Sun by a bit under a third, and that modest difference in distance, that little extra sunlight, is a large part of what tipped it into the runaway while Earth stayed cool enough to keep its seas. Which means the line between a living world and a cooked one is not some enormous gulf, only a matter of a little more heat than the thermostat can swallow. Earth today sits in the comfortable middle of the band where liquid water is possible, but the inner edge of that band, the distance at which a world tips into the Venus runaway, is not far inside our orbit, and it is creeping outward as the Sun brightens. In about 1 billion years that edge reaches us. Venus is not a freak that befell a different sort of planet. It stands as a preview of Earth with the Sun turned up, and the Sun is turning up. When you look at that pale, choking shroud, you are looking at the sky Earth grows toward as its own thermostat is overwhelmed. Venus is a planet the size of Earth that had water and cooked it off, and its own atmosphere signed the confession. Let me be honest about the uncertainties, because they are real and I will not hide them. Exactly when Venus lost its water, and how quickly, and whether it ever truly had stable oceans on its surface, or only ever a hot, wet atmosphere that never got to settle, is genuinely debated. There are models where Venus had shallow seas for 1 billion years or more, and models where it was always too hot for oceans to form at all. That argument is open, but the destination is not in doubt. Whatever the exact path, Venus ran away into a dried, cooked, carbon dioxide smothered state and has been there ever since, and it did so as a world nearly the size of ours that plausibly began with water. The uncertainty is all about the road. The wreck at the end of it is plain to see. Now the arc, because Venus does something different with it, and the difference is the point. Around Mars, the arc of air on the limb was a thin, faint tan line, a stripped remnant. Around the Moon there was no arc at all. Turn to Venus, edge on against the black, and look at its rim, and you find neither a thin line nor an absence. You find the opposite failure. Venus's limb is a thick, bright, unbroken band of pale cloud, a dense, choking shroud wrapped so completely around the planet that you cannot see the surface at all, not one feature of it, through the whole depth of that smothering air. Where Mars lost its sky by having it stripped away to almost nothing, Venus ruined its sky by having far too much of the wrong kind. a suffocating blanket that turned against the world and cooked it. Two opposite ways for the arc of air to mean death. Too little, blown to space on Mars. Too much and poisonous, holding in the heat on Venus. A world can die from either end of the same feature. So now we have both deaths in front of us as real places, not theories. Mars, the cold stripping, the sky and water blown to space when the shield fell. Venus, the hot runaway, the water boiled into the sky and lost while the surface baked under a crushing blanket. And Earth, we have already seen, has one clock pointed at each of them, the cooling core toward the Mars death, and the brightening sun toward the Venus death, which forces the question the hook left hanging, the one it is finally time to answer. When Earth's turn comes, which of these is it? Do we end cold and stripped like Mars, or scorched and smothered like Venus? The honest answer is stranger than a simple choice between the two, and it is where we go next. Earth is scheduled for both deaths in order. That is the answer to the question the whole middle of this video has been holding open, and it is stranger than the simple choice between ice and fire, because it is not a choice at all. Earth does not end as a Mars or as a Venus. Earth ends as a Venus first and then as a Mars, the fire before the stripping, because the two clocks run one after the other, and the faster one goes first. Take the near future first, the fire, because that is the one that arrives while Earth's core is still warm and its shield still up. This is the sun's clock, the brightening we traced earlier, and it does not wait for anything inside the planet to fail. In roughly 1 billion years, as the sun climbs toward about 10% brighter than it is now, the thermostat that has kept Earth temperate gives out. The slow cycle that pulls carbon dioxide from the air to fight the rising heat runs it down to a level too low for plants to live on, and the base of the living world collapses. And then the heat keeps climbing past what the oceans can bear, and the runaway begins. The very process we watched finish on Venus. Water rises into the sky as vapor. The vapor traps more heat, more oceans lift, and Earth passes into a moist, scorching, choking phase that looks far more like young Venus than like Mars, its oceans going into the air and, from there, split apart by sunlight and bled off into space. For a long stretch, Earth's ending is a hot ending. It is the fire, and it is driven entirely by the sun, and it is due in about 1 billion years, which is to say long before the core clock has even begun. And the drying does more than kill what lives on the surface. It shuts down the very machinery that kept the surface livable. Water is what eases the slide of Earth's moving plates, and a world that loses its oceans tends to lose its plate motion too, seizing up the way Venus seized up, which shuts off the carbon thermostat for good and locks the heat in. Life will not vanish all at once. As the surface becomes impossible, the last living things will retreat, first toward the poles and the high ground where it is marginally cooler, then downward, into the deep rock where a little water may still linger in the pores and the heat has not yet reached. The final biosphere of Earth will most likely be microbes, buried in the crust, the same kind of simple, tough, single-celled life the planet began with, holding on in the dark for a while after the surface has become a scorched waste of drying salt flats where the seabeds used to be. The living world will end roughly the way it started, as microbes in the rock, only this time on the way down instead of the way up. And above them the sky will hang thick and hot and heavy with the last of the vapor that used to be the oceans, on its way to being split apart and bled off to space, turning Earth by slow degrees into the dry-cooked twin of the Venus we just left. Let me lay the whole sequence out cleanly, because it is easy to lose in the overlap. First, over the next 1 billion years or so, the brightening sun pushes the surface past what the thermostat can hold. The plants fail, and the oceans begin to boil up into the sky and bleed off to space. That is the fire, and it turns Earth into something like Venus, hot and dry and wrapped in a heavy sky, while the core is still warm and the shield still up. Then, over the billions of years after that, the core finally cools, the dynamo dies, the shield comes down, and the solar wind strips that heavy sky away as it stripped Mars's, thinning the air toward nothing and leaving a bare cold rock. Fire first, then the cold stripping. Venus, and then Mars in that order on the same planet. And the honest thing to add is that the two stages blur at their edges, And which one you would call the true death depends on where you draw the line, at the last living cell, at the last drop of surface water, at the last breath of air. But wherever you draw it, the direction is fixed and the order is fixed. Earth grows hot and loses its water, then grows cold and loses its air, and at the end of both it is the rusted stillness we began the night standing on. Now here is the thing people miss, and it is why the honest answer is both, in sequence. Boiling the oceans does not finish the planet off into a Mars, it cooks it into a Venus, a hot dry world still wrapped in a thick heavy atmosphere of whatever gases are left, mostly carbon dioxide, held in by its own weight. That is a dead world, but it is not the stripped, thin-skied, rusted Mars we started this whole video on. To get to the Mars ending, the actual bare, stripped rock, you need the second clock, the slow one, the core. And that clock is still running underneath the whole time, so push further out, past the boiling billions of years further, and Earth's core finally cools enough that its dynamo falters and its magnetic shield comes down exactly as Mars's did. And now the solar wind, unopposed at last, begins to strip that thick hot atmosphere away, carrying it off to space over hundreds of millions of years, thinning the sky the way it thinned Mars's, until what is left is not a smothered furnace but a bare, cold, stripped rock under a thin remnant of air. The fire cooks the water away. Then, much later, the stripping carries the sky away, and the finished Earth, ages and ages from now, at the very end of both clocks, is a dry, stripped rock. It is Mars. The very world we opened on is the last stage of our own planet, reached the long way round through fire first and then through stripping. So the strange, complete answer is that Earth is not choosing between the two dead worlds we have visited. Earth is going to be both of them, one after the other. It becomes a Venus on the sun's clock in about 1 billion years, and then, on the core's much longer clock, that cooked Venus is slowly stripped down into a Mars. Ice or fire is the wrong question. The answer is fire, and then long afterward the cold stripped stillness. We visited Venus and Mars as two separate cautionary tales. Two different neighbours who died two different ways. They are not two different fates, they are two stages of a single fate, and it is ours, and we have already been shown both of them by worlds we can see in the sky tonight. I have to be honest about what is firm here and what is not, because the ordering is robust but the calendar is not. That the sun brightens, that it will boil the oceans, that this comes before the core death, all of that is on solid ground, and follows from physics we understand well, but the exact dates carry real uncertainty. Estimates for when the biosphere truly ends, when the surface stops being able to support life, range from a few 100 million years at the pessimistic end, to something closer to 1 billion or even beyond at the more generous end, depending on how the thermostat and the clouds and the oceans behave as things heat up. And the very last stages, whether Earth is finally left a stripped rock, or is instead swallowed whole a few billion years further on when the sun swells into a red giant and expands out toward our orbit, is itself argued over, with some recent work suggesting Earth might just survive being engulfed, and some suggesting it will not. So I am not selling you a precise timetable. What I am telling you is the sequence and the direction, and those are not in doubt. Fire first, from the sun. Stripping later, from the failing core. A living world becoming a Venus and then a Mars. Finite, ordered, and already begun. And that ordering does something important to the whole picture, so let me draw it out. It means Mars is not a separate warning from Venus, a different way things could go. Mars is the later stage and Venus is the earlier one, and Earth is scheduled to write both. When you look at Venus, you are looking at Earth in about 1 billion years, the fire stage. When you look at Mars, you are looking at Earth billions of years after that, the stripped stage, the true end. Two dead neighbours, and both of them are portraits of our own planet at two different points in its one unavoidable decline. The solar system is not full of different fates for a rocky world. It shows us the same fate at different stages, and we happen to be standing at the one stage that still has water and air and a blue arc on its edge. Which brings us, unavoidably, to the question you have probably been holding since the two clocks first appeared, the one that every honest person asks when they are told their world has an expiry date written into physics. If all of this is scheduled, if it is coming whether we are good or bad, whether we pollute or repent, then is there anything at all we could do about it? Can any of this be stopped, or slowed, or escaped? It is the right question to ask, and I am going to give you the honest answer, which is not the flattering one. No, it cannot be stopped. Not by anything we can do, and not by fixing the things we usually argue about when we talk about the fate of the Earth. That is the honest answer, and I want to give it to you straight before I complicate it, because the whole video has been building toward this correction, and it would be dishonest to soften it now. The death of Earth as a planet is astronomical and geophysical. It is written in the size of our core and the aging of our star, and both of those are on a scale that has nothing to do with us and nothing to do with our behavior. Now let me complicate it, because this cuts both ways and I refuse to let it be misused. When most people hear that Earth is heading toward a Mars or a Venus, they think of the thing we argue about every day, the carbon we put into the air, the warming we are driving right now, and they think that this video is either a warning about that, or worse, an excuse to shrug it off. It is neither, and the distinction matters enormously. What we are doing to Earth's climate is real, and it matters urgently, on the timescale that we actually live on. The warming we are causing now plays out over decades and centuries, and it is fully capable of wrecking the conditions that our civilization depends on, of drowning coastlines and breaking harvests and displacing people in numbers that are hard to think about. None of that is being waved away here. On the human timescale, on the scale of your life and your grandchildren's lives, what we do to this world is one of the most important things there is. But it is a different problem from the one that turns Earth into Mars, and confusing the two helps no one. Our emissions cannot boil the oceans into space. They cannot cool the core or bring down the magnetic shield. Even at their very worst, they operate on a scale of degrees over centuries, not the wholesale evaporation of the seas over 1 billion years as the sun itself grows hotter. The planetary death, the real subject of this video, runs on hundreds of millions to billions of years, and it is driven by forces that dwarf anything we could add or subtract. So the two things are not the same lever. One is a genuine emergency that is ours to affect. The other is a certainty that is not ours to touch. And the reason that matters is that the planetary ending has no lever at all that we can reach. Look at what you would actually have to do to stop it. To stop the core death, you would have to reach into the center of the Earth and put back the heat it is losing, refill a cooling core that is thousands of kilometers down and hotter than the surface of the sun, and keep it churning. There is no conceivable technology for that. You cannot reheat the heart of a planet. To stop the solar death, you would have to reach out and turn down the sun, slow the fusion in the core of a star, hold its brightness steady against the physics of its own aging. You cannot dim a star. These are not engineering problems that are merely very hard. They are outside the category of things a species does to a planet or a star at all. I will give you the one genuine exception because it exists and honesty demands it, though it will not comfort you much. There is a serious proposal, worked out in real physics, that instead of cooling the sun, you could move the Earth. The idea is to very gradually nudge our planet's orbit outward over enormous spans of time, using repeated gravitational tugs from a carefully steered passing body, edging Earth away from the sun as the sun brightens, so that we stay in the temperate zone rather than being overtaken by the heat. On paper it works. It would, in principle, buy the biosphere billions of extra years against the solar clock. But look at the scale of it honestly. It means routinely moving the entire Earth through space with a precision and a patience and an energy budget that make our whole present civilization look like nothing, sustained across timescales longer than humans have existed. It is a real idea, and it is real physics, and it is also so far beyond anything we can remotely do that calling it a solution is a kind of category error. And even if you managed it, it does nothing whatever for the cooling core. Move Earth as far out as you like, and the dynamo still fails on its own schedule, and the shield still comes down, and the stripping still comes for the air. You could dodge the fire and still meet the cold. People sometimes reach for even wilder fixes, and it is worth being honest that none of them close the gap. There are speculative notions of slowly stripping mass off the sun to make it burn cooler and longer, of building an enormous artificial magnetic shield out in space to stand in for the failing one, of wrapping the whole planet in engineered layers to hold its air. Every one of them, taken seriously, demands command over energy and matter so far past us that they are less plans than illustrations of how far past us the problem sits, and they all run into the same wall. This is not one failure you could patch. What faces us is a whole living world quietly running out of the two things that made it livable, its inner heat and its steady star, with no single valve to close and no one part to swap. You would have to take over the running of a planet and a star at once, and keep running them, without end. So when I say it cannot be stopped, I do not mean we have simply not yet found the trick. I mean the scale of the thing is not the scale of anything a species does, but the scale of the physics that builds worlds and burns stars, and that physics does not negotiate. Let me set the two problems side by side one last time, plainly, because the difference in scale is the whole point. What we are doing to the climate now unfolds over decades and a few centuries, and it is measured in a handful of degrees, and it is, at least in principle, ours to slow or stop, and it threatens the world of harvests and coastlines and cities that we actually live in. The planetary death unfolds over hundreds of millions and billions of years, and it is measured in the outright loss of the oceans and the air, and it is not ours to touch at all. Those are not the same story told at different volumes. They are different stories on different clocks, and the honest thing is to hold both without letting either swallow the other. The near one is urgent and ours. The far one is enormous and not ours. It would be a mistake to shrug off the near emergency because the planet is doomed in a billion years regardless, and just as much a mistake to imagine that fixing the near emergency saves the world from the far one. Tend the garden while it is a garden. That is the sane response to a world with an ending written into physics, and it is the only lever we actually hold. The other escape people reach for is simpler to state and just as hard. Leave. Take life somewhere else before the planet dies. And I will say plainly that this runs straight into a wall we do not have time to fully explore tonight, which is that there is nowhere in reach to go. The nearest worlds are the dead ones we have spent this whole video visiting, and the nearest star that might hold a better one is so far away that crossing to it is a problem of a different and probably unsolvable order. Leaving is not obviously easier than staying. It may be harder. So the honest bottom line is the hard one. The planetary death of Earth cannot be stopped by us. Not by living better, which we should do anyway for our own near-term sake. Not by any technology we can seriously foresee. Not by cooling the sun or reheating the core, both of which are simply beyond us. The most we can honestly imagine is delay at a cost and a scale that belong to science fiction, and even that only buys against one of the two clocks. This is the part of the truth that has no workaround, and I would rather hand it to you whole than pretend there is an out that there is not. And that leaves one thing genuinely open, not a fact but a judgment, and I am not going to close it for you because reasonable people land in different places on it, and it is honestly yours to weigh. If the ending cannot be stopped, only, at most, outrun, at impossible cost or fled to nowhere, then is it worth spending anything at all now on trying to outlive it? Is a species that knows its world has an expiry date a billion years out obliged to start reaching for the stars, or to start learning to move planets, absurd as that sounds? Or is a billion years simply so far off, so far beyond anything we can plan for or even imagine, that is not our problem to carry at all, and the only sane thing is to tend the world we have for the short while it is good? I have my own lean on that, but I think this one belongs to you. Sit with it. It is the one door in this whole video I am going to leave open on purpose, because it brings us back at the very end to the only question that was ever really on the table. Not whether Earth ends the way Mars did, but how far down that road we already are. So how far down the road are we? Here is the honest answer, assembled from everything we have looked at. Earth is a living world in the middle of its one moment, and Mars is the same kind of world at the end of it. And the only real difference between them is time, and the time is already being spent. Put the whole thing together, because it comes together into something simple and hard. Every rocky world runs on two things it cannot keep and cannot refill: the heat in its own core and the steadiness of its star. The heat runs the engine that makes the shield that holds the air and the water. The star, if it stays steady, leaves the surface temperate, and neither of those loans lasts. The core cools, on a clock set by the size of the world. The star brightens, on a clock set by the physics of its own burning. Both come due. Mars was small, so its core clock ran out first 4 billion years ago, and Mars shows us the finished bill. A world with no field, no air worth the name, no surface water, a rusted stillness holding its dead rivers as fossils. Earth is the same kind of world with more heat still in the tank, and a star not yet hot enough to boil its seas, so it still runs its engine, still holds its shield, still turns that bright blue arc of air to the black. But the tank is draining, and the star is brightening, and the ending is not in doubt, only its date is. That is what it means to say Mars is not our warning but our preview. A warning is about something that might happen that you could still prevent. This is not that. Mars is a photograph of home, developed a few billion years into the future. When you look at that frozen, rusted desert with its dry riverbeds, you are not looking at an alien place that suffered an alien fate. You are looking at the Earth later. The oceans that carved our seabeds will be gone the way the Martian rivers are gone. The thick blue arc on our limb will have thinned to a tan smear and then to nothing, the way Mars's did, the way the Moon's is. The living world will have gone still, keeping whatever scars it had at the end, because there will be nothing left moving to erase them. Everything we have watched happen to Mars is a rehearsal for Earth, run early, on a smaller and quicker world, so that we could stand here now and see our own future already played out in the sky. So how far down the road, really? The honest answer is that we are past the beginning and nowhere near the end. The core still burns, the shield still stands, the oceans are still here, and the blue arc is still bright, and there are, on the most generous reading, hundreds of millions to a billion or so years left before the sun's clock even begins to boil the seas in earnest, and billions more before the core clock brings down the shield and finishes the stripping. On the scale of a human life, that is a span so long it may as well be forever. On the scale of the planet, it is simply the middle. We are living in the one lit stretch a world like ours gets, the stretch between the moment it first held water and the moment it loses it for good. And that stretch, however long it feels from inside, is not the permanent condition of the Earth, only a phase, the living phase, and it is the phase we happen to have been born into. Think of it from the outside, from the position of some visitor arriving billions of years from now, and finding the stripped rock that Earth will have become. They would see a dead world, another rusted or cooked stone among the many, with no way of knowing at a glance that it had once been blue, that it had held oceans and weather and for a while minds that looked up and worked all of this out. The dry seabeds would be there, the way Mars's dry riverbeds are there now. A drainage map of a living past carved into a dead surface, waiting to be read by anyone who came late enough to see only the after. That is exactly what Mars is to us. A world whose before we have had to reconstruct from the fossils of its water, because we arrived so long after its living phase that we have only ever known the corpse. And that is what Earth will be to whoever comes after. A world remembered, if at all, only in the shapes its vanished water left behind. Which is, when I sit with it, less a reason to despair than a reason to take the blue seriously while it is here. The living phase of a world is not its normal condition that happens to be ending. Rather, it is the brief, unlikely, lit exception between two long darknesses, the emptiness before life and the emptiness after it. And we are inside that exception, now, on the one world we know of that is currently having its moment. So when I look back now at that dry canyon we started on, the great dead gash of Valles Marineris with its water gone for billions of years, I do not see a foreign wonder anymore. I see a preview of the seabeds under our own oceans, laid bare and dry, cut by water that will one day be as gone from Earth as it is from Mars. We opened tonight on what looked like another world's ruin, and it turns out we were looking at a photograph of our own future, developed early on a smaller world that reached the finish first. Every dead riverbed on Mars is a rehearsal of a dead riverbed to come on Earth. Every empty basin is one of our oceans in advance. That is what it means to say Mars is not our warning but our preview. And that is why I can no longer look at the red planet the way I once did, as simply somewhere else, because it is not somewhere else at all. Mars is here, only later. And knowing that changes what it feels like to stand on this world now, in the lit stretch, with the water still in the seas and the blue still on the edge of the sky. I want to be honest one last time about the edges, because I have tried to be all the way through and I will not stop at the finish. The exact date is unknowable. I cannot tell you whether the oceans start to go in 300 million years or a billion, whether the final stripping leaves a bare rock, or whether the swelling sun swallows the whole planet first, because the models argue and the timescales are longer than anything we can measure against. And the road has two stages, the fire and then the cold, that I have had to lay out in sequence when the truth is they blur and overlap at the edges in ways we are still working out. So do not take a number from me. But the two things that actually matter are not in doubt, and no uncertainty in the calendar touches them. The ending is finite, and it is not ours to stop. Earth will end the way Mars ended, by the same running down of the same two loans, and the process is already underway, quietly, in a cooling core and a brightening star, while the oceans are still full and the sky is still blue. Which is why when I look at Earth now, after everything we have traced tonight, the thing I cannot stop seeing is that thin blue line of air on the edge of it. We have followed that arc across 5 worlds. We watched it thin to a tan ghost on Mars, and vanish to a hard black edge on the Moon, and turn into a choking pale shroud on Venus. And we turned to Earth and found it clean and bright and blue, the living sign, the mark of a world still running. And now you know what that line is. It is not a fixed feature of our planet. That line is the visible reading on 2 clocks that are already counting down. It is beautiful, and it is temporary, and it is the exact thing that all of this is coming, in the end, to erase. Mars wore a line like that once, and so did Venus, before the shroud. Ours is not permanent either. And that is not a reason for despair, I think, so much as a reason to actually look at it, this once, and understand what we are looking at while it is still there to see. I keep coming back to that dry canyon on Mars, the one carved by water that has not run there in billions of years. When I started this, I thought of Mars as a warning, the kind of thing you take on board and act on. I have stopped thinking of it that way. Mars is not a warning. A warning is about a mistake you can still avoid, and this is not a mistake, and there is nothing here to avoid. Mars is a mirror, held up a few billion years down the line. Every rocky world runs on 2 things it cannot keep: the heat in its own core and the steadiness of its star, and both of those run out. The core cools, the shield around the world fails, the star grows hotter, the water leaves for space, and the sky thins away to almost nothing. Mars has finished that. We are somewhere in the middle of it. The hardest part to sit with for me is that almost none of it is our doing, and none of it is ours to stop. We argue bitterly about what we are doing to this world, and that argument matters for us for the short time we are here. But the planet itself was always going to end this way, with us or without us, the way Mars already has. So when I look at Earth now, the thing I notice is that thin blue line of air around the edge of it, seen from space, the one bright arc that means a world is still alive. Mars had a line like that once. It does not now. Ours is not permanent either. We are living in the short stretch of time a world gets while the light is still on. If nights like this are your sort of thing, subscribing is the way to keep them coming. Sleep well.